Welcome to another video by Adeptus Academy. Today we're diving into the fascinating world of engines. From the first steam engines of the Industrial Revolution to the jet engines soaring above us, we'll uncover the mechanics that shaped our world. We'll break down how different engines work and the principles behind them, step by step, and yes, it'll be fun. Are you ready? Let's get started! Our journey begins with a true pioneer, the steam engine. Picture a world before cars and planes, where the hiss of steam and chug of pistons powered progress. The steam engine starts with a boiler, heating water to create steam. This steam is channeled into a cylinder, pushing a piston back and forth. The piston's motion is transferred by a connecting rod to a crankshaft. The crankshaft converts this linear motion into rotation. This rotating power, generated by steam, could drive wheels, power factories, and move mountains. The steam engine's simplicity and power changed history. Now that we've seen the steam engine in action, let's take a closer look at what makes it tick. Steam engines are more than just relics of the past. They're a window into the fascinating world of heat engines, which have shaped the course of human history. At the heart of every steam engine lies a simple but powerful principle: the conversion of heat energy into motion. When we burn fuel to heat water, we create steam, and that steam holds a tremendous amount of energy. Steam engines belong to a broader family known as heat engines. These are machines specifically designed to transform thermal energy, energy from heat, into mechanical energy, which is the energy of movement. This process is at the core of countless machines we use every day. Inside a heat engine, heat is harnessed and carefully directed to push pistons, turn wheels, or spin turbines. This transformation is what allows engines to power everything from trains to factories. Think about a campfire. It gives off warmth and light, but that energy simply dissipates into the air. A heat engine, on the other hand, captures that energy and puts it to work, channeling it into useful tasks like moving vehicles or generating electricity. While steam engines use heated water as their source, heat engines can be powered by a variety of fuels and energy sources. Coal, gasoline, natural gas, and even the sun's rays can all provide the heat needed to drive these machines. The ability to convert raw energy into useful work sparked the Industrial Revolution, leading to inventions that changed the world. Factories, locomotives, and ships all relied on heat engines to operate, making mass production and rapid transportation possible. Today, heat engines remain a cornerstone of modern technology. From the engines in our cars and airplanes to the massive turbines and power plants, these machines continue to drive progress, powering our cities and connecting our world. Fast forward to the 20th century and meet the petrol engine, the heart of most cars and motorcycles. Unlike steam engines, petrol engines use internal combustion. Fuel burns inside the engine's cylinder. Petrol mixes with air, is injected into the cylinder, and compressed. A spark plug ignites the mixture, causing a controlled explosion that drives the piston down. This force powers the vehicle. The process, intake, ignition, exhaust, happens hundreds of times per minute. That's how our vehicles move with such power and efficiency. Internal combustion changed transportation forever. The petrol engine's magic lies in the four-stroke cycle, a perfectly timed sequence that has revolutionized transportation. This ingenious process is the reason our cars, motorcycles, and even some airplanes can move with such power and efficiency. Each stroke is a carefully choreographed movement, working in harmony to convert fuel into motion. Stroke 1. Intake. As the piston glides downward, it creates a vacuum that draws in a precise blend of air and fuel. This mixture is the lifeblood of the engine, setting the stage for the energy to come. The intake valve opens just at the right moment, allowing the cylinder to fill with this vital combination. Stroke 2. Compression. Now the piston rises, squeezing the air-fuel mixture into a tight space. This compression is crucial, as it increases the potential energy stored within the mixture. The tighter the squeeze, the more powerful the explosion that follows. Stroke 3. Power. At the peak of compression, a spark ignites the mixture, causing a controlled explosion. This sudden release of energy forces the piston downward with tremendous force, generating the power that turns the engine's crankshaft and ultimately moves the vehicle forward. Stroke 4. Exhaust. Finally, the piston moves up again, pushing the spent gases out through the exhaust valve. This clears the way for a fresh charge of air and fuel, ready to begin the cycle anew. Each stroke is essential, and together they transform chemical energy from fuel into the mechanical energy that propels us down the road. The pistons, valves, and spark plugs all work in perfect unison, like instruments in an orchestra. This cycle repeats at incredible speeds, hundreds or even thousands of times per minute, powering our vehicles with seamless efficiency. It's a marvel of engineering, happening right beneath our feet every time we drive. The four-stroke cycle is truly the heartbeat of modern engines, pulsing with energy and precision. Without it, our world would move much slower. It's a dance of precision and power, where every component must play its part at exactly the right moment. This synchronization is what makes modern engines so reliable and efficient. Without this meticulously timed sequence, engines would be inefficient, unreliable, and far less powerful. The four-stroke cycle is what separates modern marvels from the engines of the past. So next time you hear the hum under your car's hood, remember, you're listening to a symphony of motion, a masterpiece of engineering that keeps our world moving forward. A single-cylinder engine works, but multiple cylinders make things smoother and more powerful. Imagine pistons firing in sequence, delivering a steady flow of power. In multi-cylinder engines, each cylinder runs the four-stroke cycle independently, but their timing is staggered. This reduces vibrations and creates a smoother ride. More cylinders mean more torque and horsepower, better acceleration and higher speeds. Efficiency improves too, as fuel burns more completely. Multi-cylinder engines are the backbone of modern vehicles. They balance power, smoothness, and efficiency. That's why most cars use them today. Now let's talk about the diesel engine, famous for efficiency and torque. Diesel engines use compression. Ignition air is compressed until it's hot enough to ignite injected diesel fuel. No spark plugs needed, just intense pressure and heat. This high compression makes diesel engines more fuel efficient, especially for heavy-duty work. They deliver strong low-end torque, perfect for trucks and buses. Diesel engines extract more energy from each drop of fuel. That's why they power so many heavy vehicles. Let's simplify things with the two-stroke engine. Unlike the four-stroke, it completes its cycle in just two strokes. Intake and exhaust happen alongside compression and power, using ports instead of valves. As the piston moves up, it compresses the mixture and uncovers the intake port. At the top, ignition pushes the piston down, uncovering the exhaust port. This design makes two-stroke engines lighter and less complex. They pack a high power-to-weight ratio, more power for their size. That's why they're used in motorcycles and small machines. Now, let's take flight with aircraft engines, built for extreme conditions and reliability. Early aircraft engines were adapted from car engines but needed to be lighter and stronger. They use metals like aluminum and magnesium to cut weight. At high altitudes, thin air reduces power, so superchargers or turbochargers compress incoming air. Aircraft engines are rigorously tested for safety and durability. Reliability is crucial when you're thousands of feet up. These engines are marvels of engineering. They keep us flying safely and efficiently. Aviation wouldn't be possible without them. Welcome to the jet age, where speed and altitude redefine travel. Jet engines generate thrust by expelling high-velocity exhaust gases, not by spinning propellers. Air enters the intake, is compressed by spinning blades, and mixed with fuel in the combustion chamber. Ignition creates hot gases that expand rapidly. These gases spin a turbine, powering the compressor. Finally, the gases shoot out the nozzle, propelling the aircraft forward. It's Newton's third law in action. Every action has an equal and opposite reaction. Jet engines revolutionized aviation. Jet engines are the beating heart of modern aviation, and they come in two main types, centrifugal flow and axial flow. These two designs represent distinct engineering philosophies, each with its own strengths, challenges, and unique place in the history of flight. Centrifugal flow engines use a spinning impeller to fling air outward, compressing it before combustion. This design is reminiscent of a spinning water wheel, where air is scooped up at the center and rapidly accelerated outward by centrifugal force. The compressed air is then mixed with fuel and ignited, producing thrust. These engines are known for their mechanical simplicity and ruggedness, making them ideal for early jet aircraft and applications where reliability is crucial. In contrast, axial flow engines move air parallel to the engine's axis, using multiple stages of rotor and stator blades. Each stage compresses the air a little more, allowing for a gradual and highly efficient increase in pressure. This design is more complex, but it allows for much greater airflow and ultimately more power. Axial compressors gradually increase air pressure and temperature, squeezing every bit of energy from the incoming air. This results in higher efficiency and greater thrust, which is essential for the demands of modern high-speed aircraft. The intricate arrangement of blades and stages is a marvel of engineering, designed to maximize performance while minimizing weight and drag. Centrifugal flow engines are simpler and robust, often easier to maintain and less sensitive to foreign object damage. However, axial flow engines, with their streamlined design, are more efficient and powerful, making them the preferred choice for most commercial and military aircraft today. Most modern aircraft use axial flow engines for their superior thrust and fuel efficiency, enabling long-distance travel at high speeds. These engines have become the standard for everything from passenger jets to cutting-edge fighter planes, shaping the way we travel and connect across the globe. Yet, each design has its place in aviation history. Centrifugal flow engines powered the earliest jets, while axial flow engines drove the evolution of faster, higher-flying aircraft. Together, they tell the story of innovation and progress in aerospace engineering. The evolution of jet engines pushed flight to new heights, transforming what was once a dream into a daily reality. From test stands roaring with fire to the thunder of engines in the sky, these machines have redefined what's possible. That's the story behind the engines that power our skies. Two remarkable designs, each a testament to human ingenuity, working together to keep us soaring above the clouds. From steam to jet engines, we've explored the machines that power our world. Human ingenuity has turned heat and pressure into motion and progress. This is just the beginning. There's so much more to discover in engineering. Thanks for joining me on this adventure into the heart of engines. Until next time, keep exploring and stay curious.